A double sideband suppressed carrier modulation, or DSB-SC modulation, occurs when you take a message signal and you multiply it by the carrier signal. So right here we have MFT, which is the message, and then the A sub c times cosine of 2 pi times S sub c times t, in which A sub c is the carrier's amplitude and F sub c is the carrier's frequency. And then if you input them through a multiplier, mixer, or modulator, the output of that would be the DSB-SC signal. In the time domain, we can write the modulated signal as just the straight up multiplication of MFT and AC cosine 2 pi FC of t. To get the signal in the frequency domain, we take the Fourier transform of that, and with the modulation property, we'll get the following. Let's do an example in which a message signal MFT DSB-SC modulates a carrier signal CFT. So let's say MFT equals A sub m times cosine of 2 pi times 2t. And then the carrier equals AC cosine 2 pi times 20t. And this means the frequency of the message, or F sub m, is 2 Hz, and the frequency of the carrier, F sub c, is 20 Hz. Multiplying both of them gives us this, and we could rewrite this using the product to sum trig identity. And then just to note, it does not matter which frequency you subtract first, because the cosine is an even function, which means that the cosine of a negative argument equals the cosine of the argument. So we'll have AM times AC times half times cosine of 2 pi 18t plus cosine of 2 pi 22t. And then for simplicity, I'm going to set AM and AC to 1. To help us plot the frequency spectrum, we're going to take the Fourier transform of the cosines. So the Fourier transform of a cosine is taking half of the amplitude, multiplying it to a delta of f minus the frequency, plus half the amplitude times delta of f plus that frequency. So using that, we'll get this as the frequency response of the modulated signal. For our first sinusoid, we're taking half of the amplitude, which is 1/2, so half of 1/2 is a quarter, and we're subtracting f by its frequency 18 and adding 18, and then we also do the same for the other cosine of 22 Hz. This is what the frequency spectrum would look like. We'll have spikes of amplitude 1/4 at 18 Hz, negative 18 Hz, 22 Hz, and negative 22 Hz. For the double sideband suppressed carrier modulation on Simulink, I used 2 sine wave blocks, one of them for the message signal and one of them for the carrier. To perform the modulation, I connect both of them to a product block, and all 3 of those go into a scope so they can be viewed in the time domain. To view the signals in the frequency domain, I connected each of them to a spectrum analyzer. For the message sine wave with the frequency of 2 Hz, I set the amplitude to 1, set 1000 samples per period, and set the sample time to 0.0005. 2 Hz is 0.5 seconds in the period. If we set 1000 samples per period, and one period lasting 0.5 seconds, there would be 1000 samples in 0.5 seconds. So that means one sample would take 0.0005 seconds. For the carrier wave of 20 Hz, 20 Hz is a period of 0.05 seconds, and with 1000 samples per one period and one period lasting 0.05 seconds, one sample would take 0.00005 seconds. We can run it. To check the time domain, we click on our scope. So here's our message signal, the carrier wave, and the double sideband suppressed carrier modulated signal. And if we trace the envelope of the modulated signal, we'll have a sinusoid of the same frequency of the message signal. So here's the spectrums of the message signal and the carrier. For the message signal, we'll have spikes at 2 Hz and negative 2 Hz, and for the carrier signal, we'll have spikes at 20 Hz and negative 20 Hz. The spectrum of the modulated signal is the convolution of the messages and the carrier's frequency spectrum. So we'll have spikes at 18 Hz, 22 Hz, negative 18 Hz, and negative 22 Hz.